So, in this session we will see three things. First we will see how to change the default options, right. So, for every algorithm there is a set of default options. So, those options can be changed, right. So, if we do not give those values, even then a problem could be solved, but in many instances we may have to change the default options, right. We will look how to change the options for one of the inbuilt function, and for the rest of the other functions it is going to be similar. Right. Similarly, we will look into what is called as the use of output function. So, output function is something that is called at the end of every iteration. The inbuilt functions of MATLAB are iterative techniques, right. So, if we want the technique to do something after every iteration, we can write it in a function file and we can specify that as part of our options. So, whenever an iteration is completed, the function file which we wrote will be executed. After looking into the output functions, we look into vectorization and parallelization. So, you can find optimization toolbox as an app over here, right. So, over here you have optimization. So, if you click on this, it will open the optimization GUI, right. So, here we can select the solver. So, the functions which we have seen are listed over here. So, for example, fmin_con, we did not look at fmin_max, we did fmin_search, fmin_unc, we did GA, linprog, right. So, all those functions which we studied as part of this session are listed over here, right. So, let me say that I select GA function, right. So, if I select GA function, you can see that these are the various options, right. When we learnt the inbuilt function GA, you would have seen that we did not even specify the number of iterations, the population size or anything, right. So, that is because MATLAB by default has some values. So, these are the options that are given to the user, right. So, for example, we can change the population type, right. So, there are various types of population. We can also define our own population, right. So, that can be selected. So, the default type is double vector, right. So, the population size is default is 50 for 5 or fewer variables, otherwise it is 200, right. So, if it is a 3 variable problem, the population size is 50. If it is a 10 variable problem, the population size is 200. Even if it is a 1000 variable problem, the default population size would be 200. Right. So, similarly, there are lot of other options which are given over here. These options can be changed as per the requirement of the user, right. So, coming over to this side, here we can give the fitness function, the number of decision variable, here we can give the coefficient matrix of the linear inequalities, here we can give the coefficient matrix of the linear equalities, we can give the lower bounds over here, the upper bounds over here, non-linear constraints, we are supposed to write it in a function file and then provide the name of the file over here. And then this is the int_con which we have seen, right. So, if let us say the 3rd, 8th and 9th variable are integer, we are supposed to provide 3, 8, 9 over here, and then if we give the start, it will run and it will display the results, right. One reason why we did not use this optimization tool was that for problems involving larger dimension, we feel that it is difficult to use this optimization tool, right. So, even for genetic algorithm, if you remember the discussion in the course, since it is a stochastic technique, we need to implement 10 runs, right. At least to us it is not clear how do we implement 10 runs over here, right. Whereas the script file and the function files which we showed, we can just put a loop over there, right, and we can use it for multiple runs and also do statistical analysis, right. So, over here these are the options which we can change, right, and over here the explanation of each of them is given. So, for example, population type, if you want additional detail on population type, you can look into this help, right. So, what we will do is we will solve a problem wherein we change the default option, right. So, we will demonstrate it for genetic algorithm, right, but you can use it for any other problem, right. So, the function that we require is optim options, right. So, if you type doc space optim options, it will open the help window of optim options, right. So, this is the help window of optim options, right. So, the syntax of optim option that we will be using as part of this course is this one, right. Options is just a variable name, we can give any variable name, right. This optim options is the inbuilt function, right. So, we need to use the same thing over here, and then we need to provide the solver name. Solver name means the underlying optimization function which we are using. So, for example, GA, particle swarm, linprog, int_linprog. So, whatever that function we are using, right. So, we need to provide name of that inbuilt function, right, and for each of this inbuilt function there are certain values which can be provided by the user, right. So, for example, if we scroll down over here, so the name value pair arguments are given over here. So, for example, if we are using let us say GA, right. So, in GA what are all the things which we can change? can be obtained from this options, right. So, now it is opening the options of GA. So, if you look over here, this is the option, right. So, for example, we can change the constraint tolerance, right. So, the name of the field is constraint tolerance. What it indicates is given over here in this description, right, and what is the default value is also given. So, the default value is 10 power minus 3. So, if we want to change, whatever value we want to give has to be a positive scalar, right. So, this is the keyword, this we cannot change, right. This is the description, right, which tells us what is that exactly this keyword corresponds to and what are the possible values and what is the current default value, right. So, the current default value is in this curly braces. So, for example, over here we have maximum generations, right. So, if we want to modify the maximum number of generations, we need to provide this keyword max generations, right, and provide a positive integer, right. So, the default value is 100 into number of variables. So, if we have a 5 variable problem, the default value is 500 generations. If it is a single objective optimization problem and we are using the function GA, if it is a multi-objective genetic algorithm, then the maximum number of generation is 200 into number of decision variables. So, this is a function file. This helps in creation of the offspring using mutation. So, the different options which are available for mutation is given over here, mutation options, right, and the default option is mutation Gaussian. If we are working with GA, right, if we are working with GA multi-objective, then the default option is mutation adapt feasible, right. So, if we click on this mutation options, we will get additional information on mutation options. So, now what we will do is we will solve an optimization problem. So, here what we will do is we will not solve with default GA, right. We want to solve with the inbuilt function GA, but we want to work with a crossover probability of 0.6 and we also want a plot which will plot the iteration versus best objective function value. So, what we will do is we will create a function file, right, wherein we will write the objective function, right, and then this is the script file, right. So, all this we have discussed, right. So, now what we are doing is we are defining a variable options, right, and we are using the inbuilt function of MATLAB optim options, right. So, this has to be only optim options. Instead of this options we can have, let us say, GAOPT, right, because this is just a variable name, right, but this optim options is an inbuilt function. So, that has to be called as such, right, and now we want to solve with GA and we want to change the default values of the GA function. So, we need to give this GA within single quotes, right, and then in this plot FCN, right. So, there are a lot of plots that GA can generate. If you look at the options of GA, you will be able to see plot FCN, right, and then we are selecting this one. Again, this is an inbuilt function which is already available, right. We are changing the value of plot FCN, right, to GA plot best F, right. Similarly, we are changing the crossover fraction to 0.6. The keyword which corresponds to the crossover fraction is crossover fraction and we are changing the value to 0.6, right. So, if we go over here, right, and look at the options of genetic algorithm, genetic algorithm options are here. Over here we are interested in the plot function. So, this is the keyword plot FCN. For the keyword plot FCN, we could take any of these values, right. So, the default value is a null set, right. So, that is why it would not plot anything, right. So, we can take GA plot distance, GA plot genealogy. So, what we have actually taken now is GA plot best F, right. You can actually go and look into this plot options and try to understand what each of this plot is doing. So, for now we are directly giving the value. Since this is a function, we need to give this @ symbol, right. So, now since we have defined it as options, we need to solve the problem, right. So, GA fun, because that refers to this objective function file which we have written, right. D is the number of variables. We do not have any linear constraints. So, no linear inequalities, no linear equalities. Lower bound and upper bound we have minus 5.12 to 5.12. We do not have any integer variables, we do not have any non-linear constraints. So, that is why all of this is empty, and then we have given options, right. So, either options, if we have used options over here, or over here we need to give GA opt, right, that is the name of the variable. So, whatever we have discussed is actually coded over here, right. So let us say initially we are running it without the options, right. So let me just comment this line, no options, right. Now if we run this, so in this case we did not change the default option, right. So it did not plot anything, right. At the completion of the algorithm it gave this status message, right, and that was it, right. So now we are changing the default option, right. So let me solve this one, right. So just because we are defining options here does not mean it will be taken by GA, right. So it will be taken by GA only if we include this options while solving GA, right. So this line was actually uncommented when we had executed line 12, right. Still we did not get any plot, right. So that is because we did not include options, though we had defined it, we did not include it. Here we are now including that. So over here if we run this now, right. So here if we see, it is actually changing, the values are changing, and every generation we are getting this plot, right. So in this case it is plotting the best value in the every generation and the mean of the fitness function of the population, right. So this way you can change the default options, right. So as part of this course it is not possible to run you through all the options, right. So here we have just demonstrated that the options can be changed. So for whatever function you are working with, you need to go and look at what are the default options, and if you want to change them, you can change them, right. So the purpose over here is to just demonstrate that the options can be changed, right. As and when you are working with a solver, right, you can look at the default options and change whatever is required. So that was about how to change the default options of MATLAB. Now we will look into how to make use of the output function in MATLAB. So for changing options we demonstrated it with GA. So same thing we will do for output function, we will demonstrate it with GA. So for whatever inbuilt function you are using in MATLAB, you can write your own output function as per your needs. So the use of this output function is to retrieve output from an optimization algorithm in every iteration. If we specify to the algorithm through the options, right. So options is a name of a variable over here. So that has to be set using optim options, which we discussed earlier. So in optim options, if we specify the name of the solver, and if we use this keyword output FCN, right, with O and F as uppercase, that is a keyword, right, and specify name of any function file which we have written. So remember, this is not an inbuilt function file, right. So this is a function file that we are writing. So whatever changes we want, we can implement through this output function. So in case of GA, when this function file is accessed, so GA would supply these three values: options, the state, and a flag. So options is a structure which will contain the current setting used in GA, right. State will have various things. So for example, current population is also a part of state, right. So state is going to be a structure. So this variable flag denotes the current status of the algorithm, right. The syntax of the output function, if we are using GA, is whatever the name of the function that we want to give. Remember, this is a function that we write, it is not an inbuilt function. So whatever function name we give, we will receive three things. So the function that we write should be capable of receiving three things: options, state, and flag, right. And what the function is supposed to return is the state, the options, and we need to specify if we have changed the options, right. So op change is a flag which has to have a value of 1 or 0, right. So we need to provide a value of 0 if we are not changing the current options of GA. If we are changing the current options of GA in this output function, then we have to give a value of 1 to this variable OPT changed. So remember, these are just variable names, right. So we can have x, y, z and ABC over here. So here this is the fitness function, we are solving the RAS engine function. So this is something that we have done previously, right. So here we are writing a function file, right. So function file which can receive options, state, and flag. So this is with respect to GA, and this function file which we are writing will return state, options, and whether the options are changed or not using this variable OPT changed, right. So OPT changed, we are assigning a value of false over here, right. So we are assigning value of 0 or false because over here in this output function file we are not changing the options, the current options of GA. So that is why we are passing this value of false back to the algorithm, right. So what we are doing is we are accessing the population, right. So state contains lot of information. So the current population can be accessed by state dot population, right. So all of it would be assigned to variable current pop, right. So, this Rastringen function we are solving for a 2 variable. The population, if you see, it will have 2 columns, right. The first column will be for variable 1, the second column will be for variable 2, and the number of rows would be the number of solutions, right. So, what we are doing is we are plotting x1 and x2 with a blue color dot. So, what we essentially want to do is at the end of every iteration we want to see how the points are moving in the search space. If you can recollect, this we had done long back while we were looking at teaching learning based optimization. We also looked at the decision variable space as to how the solutions are approaching the optima. So, hold on is to just make sure that the plot is retained. Subsequent population is also plotted on the same plot, right. So, draw now will immediately draw the plot, right, and then we are assigning x label and y label as variable x1 and variable x2. So, now we have this objective function file ready, we have the output function file ready, right. So, now we can solve with GA. So, RNG 1 comma twister will help us to reproduce the result. So, the objective function file which we had written has a name of Rastringen. So, that we are assigning to a variable fun, right. So, the dimension of the problem is 2, we are defining the lower and upper bounds, right. The lower bound of both the variable is minus 5.12 and minus 5.12. The upper bounds of both the variables are 5.12 and 5.12, right. So, remember the GA function by default does not go into the output function file, right, unless we inform GA through options, right. So, right now we are defining options. So, this is a variable name, we are using the function optimoptions, right, the name of the solver that we are currently working with GA. So, if you are working with fmincon, then you need to give fmincon. This output FCN is a keyword, it remains the same, right, and the file that we want GA to execute at the end of every iteration is this one, which is what we previously wrote, right, output fn example, right, and then we are also changing the default crossover fraction to 0.6. Again, this is a keyword, right, it has to be a scalar value. So, we are providing a value of 0.6. So, then we solve using GA, right. So, for solving GA, the syntax is the fitness function file, number of decision variables, linear constraints if we have any. So, in this case we do not have any linear constraints. So, we give empty bracket, lower bound, upper bound. In this case we do not have nonlinear constraint. If we had nonlinear constraint, we need to give the name of the file, right, and intcon. Intcon is if we have any integer variable. So, in this case we do not have any integer variable. So, we give an empty bracket, comma options, right, options because we used the word options over here. If we had used let us say z over here, we have to provide z over here. So, when we execute this, right, we will get something similar to this, right. So, the x axis is the variable x1, the y axis is the variable x2, and it shows the variables moving, right. So, let us execute this. These are the functions which we have, right. So, this is the same thing that we explained you, the output function, this is the objective function, the Rastringen function, and this is the file that we want GA to execute at the end of every iteration. Remember, this is a file that we have written over here. So, if we execute this one, so at the end of every iteration it is supposed to plot. So, here if we see, the solutions were moving before it converged to a particular value. So, we can also put a let us say a pause of 0.01, right. So, and then if we execute this, right. So, now if you can see, this is how the solution move towards the final solution, right. So, this is the use of output function, right. So, for example, let us just put a breakpoint over here and execute this, right. So, if you want, you can either look at the help of MATLAB, right. In this case, we will just say what is state, right. So, this came at 0th iteration, this is the starting time, this is the last improvement time. So, the number of functional evaluations which it has employed may be 50, right. So, this is the population, right. So, here if we see state dot population. So, this is the population when GA comes into this function for the first time, right. If you are interested in score, you can look at state dot score, right. So, this is the fitness function value corresponding to these solutions. Similarly, you can look at the help of GA and see what are the things that are available through state and which of these things can be modified. Let us just say continue, right. So, this is the second time, right. So, here if we look at state, right, at the end of first generation. So, the best solution currently is 5.41. So, if we give continue. So, after these iterations, now let us have a look at state, right. So, at the end of these many iterations, the best value that we currently have is 1.46, right. So, here whatever changes we want to make to the current population can be made, right. In addition to whatever GA has done to generate a solution, we can employ whatever knowledge we have about the problem over here. Whatever we include over here will be taken into account by GA every time it completes an iteration. Remember, this happens only at the end of every iteration. So, now that we have seen output function, right, now let us look into vectorization and parallelization. So, vectorization we have previously discussed, right. A vectorized objective function is one which can receive n solutions, right, and evaluate the fitness function of all the n solutions and pass n values for the fitness function, right. So, for example, in this case the x can be n cross d, right, n solutions which correspond to the row and d decision variable which correspond to the columns, and it should be able to send back n cross 1 vector, right. So, here basically what we are doing is we are writing a for loop wherein we are evaluating the fitness function for each of the solution, right. So, this is a vectorized code. So, this is a example for a code which is not vectorized, right. So, in this case we have this name Rastringen, it can receive only one solution. So, it will receive one row and d columns, and it will send a 1 cross 1 scalar which corresponds to the fitness function of this particular solution. So, in this example what we will do is we will compare the performance of GA, right, with respect to a vectorized code and then code which is not vectorized. So, these statements by now you understand, right. So, we are taking a population size of 2000, right. So, by default GA has a population size, right. So, we are overriding the default option, right. So, the name of the solver, the appropriate keyword, so in this case population size, and then value for that. We are using the function optim options to set this, and we are defining it in a variable options, right. And then we have this objective function Rastringen, right. So, this Rastringen, if you remember, is not a vectorized code, it can receive only one solution at a time. We are using this tick function in MATLAB, right. So, that is similar to starting a stop clock, right. So, we are executing GA, right. We are providing the name of the fitness function, the number of decision variable, there are no constraints, the lower and upper bound, there are no nonlinear constraints and integers, and we are providing this options. So, in this case MATLAB will solve this problem using this function which is not vectorized with a population size of 2000, right, and at the end we are having this talk which is more like stopping the stop clock, right, and the time required to complete execution of this is stored in this variable NOVEC, right. So, that will tell us the time required for solving this problem without vectorization, right. So, now we want to use a code with vectorization. So, we need to explicitly inform the inbuilt function GA that the code which we have for objective function is actually capable of evaluating n solutions, right. So, again we use this optim options, the solver which we are currently working with is GA, right. So, over here this is the keyword use vectorized. So, we need to give a value of true over here. So, in this case what GA would do is every time it wants to access the objective function, it will send all the solutions together, right. In the previous case it will send the solution one by one, in this it will send all the solutions together, right, because we have used this option use vectorized and we have given true. Since we used a population size of 2000 over here, we also use a population size of 2000 over here. So, this is as usual defined in a variable, in this case again options, right, and the objective function file which we have now is Rastringen vectorized, right. So, in this case we want GA to use this file because this is a vectorized code, and we are informing GA through this options that the code that we have is a vectorized code, right. Similarly, if we measure the time with tick and talk, right, and use the same line which we had over here, it will solve the problem. And if you look at the performance, depending upon your problem complexity and the population size, you can get reasonably quicker results, right. So, without vectorization it required 17 seconds on a machine of this configuration, whereas with vectorization it required only 13.65 seconds to solve on this particular machine. So, as you can understand, it is good to have a vectorized code. First we had seen the feature of providing options, right. Then we looked into the feature of using the output function. Then we had discussed on vectorization. Now we will discuss on parallelization, right. Earlier in this course we had discussed some part of parallelization, right, wherein we had used the parfor command to parallelize the evaluation of the objective function, right. Here we are going to see the parallelization feature of the inbuilt functions of MATLAB. So, many inbuilt optimization solvers in MATLAB like GA particle swarm optimization supports this parallel computing, right. So, this parallelization is available to compute the fitness as well as the nonlinear constraint function in parallel. So, there is a difference between vectorized and parallelization, right. As we have seen earlier, in vectorization what we do is we pass this n cross d matrix together, right. So, n is the number of population and d is the number of decision variables in the optimization problem, and the objective function or the fitness function was supposed to return n cross 1, right. So, this is the vectorization feature. So, if we have the vectorization feature as on, right, then we cannot use the parallelization. So, this is the keyword of MATLAB, use vectorized. Similarly, the keyword for using parallel computing in MATLAB with respect to the optimization solvers is use parallel. If use vectorized is given as true and we also set use parallel as true or even if it is false, right, in both cases it uses the vectorized feature, it does not do parallel computing, right. So, if you want to do parallel computing, use vectorized has to be false. Here as shown, if use vectorized is equal to false and if we have use parallel as true, then it uses parallel computing. If use vectorized is false and if use parallel is also false, then it uses serial computing, right. In these three cases we will not get the benefit of parallel computing. So, for us to use parallel computing, we need to use parallel as true and use vectorized as false. So, for using parallel computing, we need to go through optim options, which we have previously seen, right. So, optim options is the inbuilt function of MATLAB. So, for whatever solver we are working with, let us say GA, particle swarm, pattern search. So, whatever solver we are working with, we need to give the name of the solver and then we need to use this keyword use parallel and set the value of use parallel as true, right, and we need to set this value of use vectorized as false, right. So, in this case it will use the parallel computing feature. So, here we will show you an example, but there is also another example given by MathWorks wherein they have a optimization problem involving ordinary differential equation and they use parallel computing to solve it. If you are interested, you can also look into that example. So, here what we are doing is we are taking the same Rastringen function which we have discussed previously, right. So, here if you carefully study this function, right, you will be able to realize that this is not vectorized, right. At a time we will be able to pass one solution, that is we will be able to pass 1 cross d and what we will get is 1 cross 1. So, every time we pass a single solution and we get the fitness function value of that solution. This we have discussed multiple times, so we will not again look into that. As we had seen earlier, parallel computing is usually beneficial when evaluation of the fitness function is time consuming. So, here we are artificially making it expensive by adding a pause of 0.01, right. So, after executing these lines, MATLAB will pause for 0.01 seconds, right, before it returns the value of f to the function which is calling it, right. So, this is our fitness function file. So, these things we will skip, by now you should be familiar with that. So, what we are going to do is solve the problem twice, right. So, first time we will solve it without parallel computing and the second time we will solve it with parallel computing, right. In both the cases we will measure the time required for solving the problem, right. So, here we are starting tick, right, and we are executing GA. So, we are providing the function which is Rastringen over here, the number of decision variable, there are no linear equalities or inequalities, hence we are providing empty brackets and then we provide lower and upper bound, right. So, when it encounters this talk, it reports the time elapsed since calling this function tick. So, basically this variable WO par will display the amount of time taken for solving this problem without parallel computing. So, here if you see we have not changed the options. So, by default parallel computing is off, right. So, then what we will do is we will use this optim options function of MATLAB, right. So, currently we are working with GA, right. So, we are providing the name of that solver GA and we are setting the value of use parallel as true and use vectorized as false. So, in this case what it will do is it will employ parallel computing, So, for us to use parallel computing, we need to first start the parallel pool, right. So, we are using this MATLAB inbuilt function pair pool. So, depending upon the settings, right, pair pool will initiate multiple workers, right. The more the number of workers, the work can be delegated to a larger number of workers. So, pair pool will initialize all the workers, right, and then again we are solving the problem between a tick and a talk, right. So, in this case we are providing the same set of inputs which we provided over here. So, for us to provide these options, we also need to specify whether we have nonlinear constraints or not, or if we have integer variables. So, in this case we do not have nonlinear constraints and we do not even have integer variables. So, again we give empty brackets and then we provide this options, right. So, options is the name of a variable which we used over here. So, now when we compute this, right, the time taken for solving this problem will be stored in W pair. So, when we executed this on a machine of this configuration, this was the time difference that we could observe. With parallel computing, it required 123.61 seconds, right, and without parallel computing, it required 853.02 seconds, right. In this case, if you want to have the same result from this solution procedure and this solution procedure, you can again fix the seed to 1. So, RNG 1 comma twistor, right. So, when MATLAB solves for the second time over here, it will use the same set of random numbers which it used for solving the first time. So, in this case, if you see the x value and f val value over here as well as the x value and the f val value over here will be identical. So, this is how you can use the inbuilt feature of parallel computing for the inbuilt optimization solvers of MATLAB. In this session, we have seen 4 features, right. First, we started with the options feature, then we looked into the output function, we followed it with vectorization of the objective function, and then we discussed parallelization of the objective function, right. Here we have demonstrated it for GA, but this discussion holds good for many of the functions which we have seen earlier. With that, we will conclude this session. Thank you.